Welcome to Electron. Now let's talk about turbines in Bernoulli's equation. While pumps deliver energy to a system, turbines, they remove energy from a system. It's the flow of the water in the pipe that drives the turbine, and by doing so, the turbine removes energy out of the system. Now, we can think of it as the turbine pushing back against the flow of the fluid. If we think the fluid as being water, of course, it would be pushing against the flow of the water. And so think of it, turbines remove energy from a system. We can think of turbines as being pumps in reverse. So everything should be exactly the same, except instead of adding energy to the system, we're removing energy from the system. And yes, there's an efficiency factor that the amount of usable power we get out of the system by utilizing a turbine is not going to be quite as much as the total amount of energy absorbed. So the power absorbed times the efficient factor will be the percent usable power. So it's 90% efficient. We only get 90% of the energy from the system and turn that into the power. Of course, 90% is still pretty good. Now here's Bernoulli's equation. Notice we still kept the term, the pressure from the pump, but we added on the right side the pressure caused by the turbine. So the turbine has a pressure term inside the equation as well, but it's on the right side of the equation because we're removing energy. So here we have what we call the frictional head loss, that is the removal of energy, and also a turbine in there is going to remove energy. That's why it's on the right side of the equation. So now we're going to relate the power absorbed by the turbine to the pressure term P sub T. How do we do that? Exactly the same way. We start with the definition of power, which is work over time. Work is force times distance, and distance divided by time is velocity. So essentially, the power absorbed by the turbine is equal to the force applied by the turbine times the velocity of the fluid. But of course, we don't want it in terms of the force, we want it in terms of the pressure. So now we're going to relate pressure to force, knowing that pressure is force divided by area, or force is pressure times area. So in this case, we want to talk about the pressure of the turbine, or the pressure that the turbine exerts on the system. So therefore, we're going to replace the force by the pressure of the turbine times the cross-sectional area. And then, of course, area times velocity can be written as the volume of fluid flowing per unit time. And then when we solve, and of course, we need to change the equation here. It's no longer the pump, it's now the turbine that we're concerned about. So now we know that the power of the turbine can be written as the power absorbed by the turbine, or I should say the pressure of the turbine can be written as the power absorbed by the turbine divided by the amount of fluid flow per unit time, or if you rather have it in terms of A times V, you can say that the pressure provided by the turbine is equal to the power absorbed by the turbine divided by the cross-sectional area and divided by the velocity of the fluid. And so just like with the pumps, the turbine conversion from power to pressure is exactly the same, just works in opposite direction, and we're removing energy from the system instead of adding energy to the system. And that's how we deal with both pumps and, in this case, turbines in Bernoulli's equation.